Conductors. The solids which have conductivities range from 10 raised to 4 to 10 raised to 7 per ohm meter are known as conductors. Metals have conductivity in the order of 10 raised to 7 per ohm meter and hence are the best conductors of electricity. Conduction of electricity in metals. Metals like gold, copper, aluminium, etc. are very good conductor of electricity. They can conduct electricity both in solid and molten form. The extent of conductivity in solids depend upon number of valence electrons. In metals, the valence band is partially filled and usually overlaps with the empty conduction band in such a way that there is no forbidden gap present. As a result, the electrons from the valence band can easily move to the conduction band. This results in conductivity in metals. Insulators. Those solids which do not allow electricity to flow through them are known as insulators. Conduction of electricity in non-metals. Non-metals like plastic, rubber do not conduct electricity. In these solids, the valence band is full while the conduction band is empty. Even the forbidden energy gap between the valence and conduction band is large. As a result, huge amount of energy is required to excite the electrons to the conduction band. Practically, it is impossible to provide this huge amount of energy to excite electrons and conduct electricity. Therefore, most of the nonmetals are insulators. Semiconductors. The solids which have conductivities between conductors and insulators ranging from 10 raised to -6 to 10 raised to 4 per ohm meter are called semiconductors. Conduction of electricity in semiconductors. The conductivity of semiconductors like silicon, germanium, etc. are based on temperature and addition of impurity. In semiconductors, the valence band is almost full, while the conduction band is mostly empty. The forbidden energy gap is quite narrow. Thus, the heat energy available at room temperature is sufficient to excite some of the electrons from the valence band to conduction band, which results in the conduction of electricity to some extent. The conductivity of semiconductors increases with increase in temperature, since more electrons can jump to the conduction band. Now, let us study types of semiconductors and how conduction of electricity takes place in semiconductors. Types of semiconductors. These are two types of semiconductors. Intrinsic semiconductors. The semiconductors which can conduct electricity in their pure form are called as intrinsic semiconductors. At room temperature, the conductivity of these semiconductors are quite low. Example: germanium and silicon are intrinsic semiconductors. The process of adding small amount of impurity to an intrinsic semiconductor is known as doping, and the impurities are called dopants. Extrinsic semiconductors. The semiconductors which are formed by adding impurity to an intrinsic semiconductor are known as extrinsic semiconductors. Example: when germanium is doped with arsenic as impurity, it becomes extrinsic semiconductor. Now, we know what is doping. Let us study how an intrinsic semiconductor can be doped. Doping can be done in two ways: with electron-rich impurity or with electron deficiency impurity, as compared to the intrinsic semiconductor. Electron-rich impurities. Both silicon and germanium belong to the group 14 of the periodic table and have 4 valence electrons each. When silicon is doped with small amount of group 15 elements such as phosphorus, arsenic, its electrical conductivity increases. In pure silicon, each silicon atom uses its 4 valence electrons for the formation of 4 covalent bonds with the neighboring silicon atoms. When silicon is doped with some group 15 elements, then some of the positions in the lattice are substituted by atoms of group 15 element. The group 15 elements have 5 valence electrons. After forming the 4 covalent bonds with silicon, one excess electron is left on them. Since this electron is not involved in bonding, it becomes delocalized and contributes to the electrical conduction. Silicon doped with the group 15 elements is called an N-type semiconductor. The increase in conductivity is due to negatively charged electrons. Therefore, semiconductor doped with electron-rich impurity is called N-type semiconductor. Electron-deficient impurities. Electrical conductivity of silicon or germanium can also be increased by doping with group 13 element such as boron, aluminium, or gallium. Group 13 elements have only 3 valence electrons. When silicon is doped with some group 13 elements, then some of the positions in the lattice are substituted by atoms of the group 13 element. The group 13 elements have only 3 valence electrons. Thus, they form only 3 covalent bonds with silicon. One of the valence electron of the silicon remains unpaired. This causes an electron vacancy or electron hole in the system. To fill this vacancy, an electron from the neighboring atom jumps into an electron hole, creating an electron hole at its original position. When the electric field is applied, electrons migrate towards the positive electrode by filling the holes, making it appear as if electron holes are migrating towards negative electrode. These holes are responsible for electrical conduction, and the resultant semiconductors are known as P-type semiconductors. Effect of temperature on electrical conductivity. Electrical conductivity of metals decreases with the increase of temperature, whereas the conductivity of semiconductors increases with increase in temperature. Why? In metallic crystal, the electrons are free to move throughout the crystal. However, the metal ions are fixed in position and can only vibrate. When a metal is heated, the metal ions start vibrating more vigorously, and as a result, motion of the valence electrons through the crystal is hindered. Thus, electrical conductivity of metals decreases with increase in temperature. In semiconductors, the energy gap is very small. a slight increase in temperature, or on the application of small voltage, some of the electrons from the valence band jumps to the conduction band and show low conductivity. Substances exhibiting this type of behavior are known as intrinsic semiconductors. Examples: silicon, germanium, etc.
Magnetization of material. Matter is made up of atoms, which are made up of electrons and a nucleus. The electrons revolve around the nucleus in a circular orbit, just as current-carrying loop constitutes magnetic dipole moment. Electrons moving in these orbits also constitute magnetic dipole moment. Beside the orbital's motion, the electrons also have a spin motion along an axis similar to Earth's rotation. This spin also constitutes a magnetic moment which has a fixed magnitude of 9.285 into 10 to the power minus 24 joule per Tesla. The nucleus has a magnetic moment, but it is very negligible when compared to that of electrons. The resultant magnetic moment of an atom is the vector sum of all the magnetic moments in an atom. The resultant magnetic moment of an atom depends on the number of unpaired electrons in the atom. Some atom contains paired electrons in all their orbitals. For the sake of understanding, let us consider helium atom, which contains only one pair of electrons. The paired electrons have orbital motion and spin opposite to each other. Due to this, the magnetic moment of paired electrons have some magnitude but have opposite direction. The magnetic moments would then cancel each other out, and the resultant magnetic moment will be zero. Some elements have unpaired electrons in their orbitals. In such atoms, the magnetic moment of the unpaired electron is not cancelled due to the absence of the paired electron. Due to this, the resultant magnetic moment in the atom will not be equal to zero. The atom behaves like a tiny bar magnet. Every material consists more than one atom. Generally, the magnetic moments of these atoms are randomly oriented and the net dipole moment of the material is zero. However, when the material is placed in external magnetic field, the magnetic moments of these atoms tend to align themselves to the magnetic field and develop a net magnetic moment. Now let's discuss about an important term called magnetization, also called as intensity of magnetization. When a magnetic material is subject to magnetizing force, the material becomes magnetized and develops a net magnetic moment that is not equal to zero. The intensity of magnetization helps us to measure to what extent the material is magnetized. It is defined as magnetic moment developed per unit volume of the material placed in the magnetizing field. Magnetization is equal to magnetic moment by volume. Magnetization is a vector quantity and its SI unit is ampere per meter. Before continuing the topic, let us learn about few terms. Magnetic flux density. Magnetic flux density is the measure of the number of magnetic field lines passing through the unit area normally. It is also known as magnetic field. It is a vector quantity and it is denoted by symbol vector B. Diamagnetism. In diamagnetic materials, the atoms contain fully filled paired electron orbitals. The vector sum of magnetic dipoles of all orbital electrons is zero. Hence, no permanent magnetism is found in such substances. At atomic level, the electrons revolve around the nucleus due to the centripetal force acting on it that is directed towards the center. Also, the velocity of the electron depends on the magnitude of centripetal force acting on it. When the diamagnetic material is placed in an external magnetic field, each of the orbital electrons experience a mechanical force called Lorentz force. The direction of the Lorentz force depends upon whether the electron is moving in clockwise direction or anti-clockwise direction. If the electron is moving in anti-clockwise direction, the Lorentz force acting on the electron will be in radially outward direction. Since these two forces are acting on the same line and in opposite direction, the effective centripetal force acting on the electron will decrease. Due to this, the velocity of the electron will also decrease. Hence, due to decrease in velocity, the magnetic dipole moment of the electron will decrease. On the other hand, in the case of electron which is moving in clockwise direction, the Lorentz force acting on the electron will be radially inward direction. Since these two forces are acting on the same line and in same direction, the effective centripetal force acting on the electron will increase. Due to this, the velocity of the electron will also increase. Due to increase in velocity, the magnetic dipole moment of the electron will increase. Similarly, all the electrons in various orbits experienced a change in magnetic moment. Some become short and some become long. Due to this, the atom develops a net magnetic moment in the direction opposite to that of the applied field. Paramagnetic materials. The atoms of paramagnetic materials have unpaired electrons in their orbits, due to which they have a permanent dipole moment. In the absence of external magnetic field, the magnetic moments of atoms are randomly oriented and the net dipole moment of such material is zero. When an external magnetic field is applied, the magnetic dipoles experiences a torque and tries to align in the direction of the applied magnetic field. At the same time, the thermal energy of the material opposes the alignment and tries to keep the dipoles in random orientation. Due to the opposing factors, only small number of dipoles align in the direction of magnetic field, and the magnetization intensity of that material will become non-zero. The magnetization of paramagnetic material depends on two major factors: temperature and external magnetic field. As the magnetic field increases, more number of dipoles can overcome the thermal energy and align with the magnetic field. The magnetization of the material increases. When temperature of the material is decreased, the thermal energy of the material decreases. Now, more number of dipoles can overcome this lower thermal energy and align with magnetic field. The magnetization increases. Again, if the temperature is increased, the thermal energy of the material increases. Now, some of the dipoles that already were aligned experience higher thermal energy and become randomly oriented. The magnetization decreases. Now, instead of external magnetic field B, it would be appropriate to use the term magnetic intensity H, which is the actual source of magnetic field. It is given by H is equal to B by mu. Therefore, we can say that the intensity of magnetization of paramagnetic materials is directly proportional to the applied magnetic intensity and inversely proportional to the absolute temperature. M is proportional to H by T. Removing the proportionality sign, the equation can be written as M is equal to C into H by T. Here, the constant of proportionality C is called Curie constant. Now let us discuss about an important term in magnetism called magnetic susceptibility. The magnetic susceptibility of material indicates how much a substance becomes magnetized when it is placed in an external magnetic field. It is denoted by this symbol, chi-m. Magnetic susceptibility of material is defined as the ratio of intensity of magnetization M to the applied magnetizing force H. Chi m is equal to m by H. Since H and m have same units, the magnetic susceptibility is a unitless quantity. Now, if we consider this relation, m is proportional to H by T. This relation can be rewritten as m by H is proportional to 1 by T. Now let us replace m by H by magnetic susceptibility. Now, from this relation, we can say that magnetic susceptibility of a paramagnetic material is inversely proportional to absolute temperature. This relation is called Curie law in magnetism. The Curie law has certain limitation. Let us discuss about it. Earlier we have learned that the magnetization of paramagnetic material increases with increase in applied field. The magnetization also increases when the temperature of the paramagnetic material decreases. In both of these cases, after a particular point, the magnetization does not increase even after increase in field or decrease in temperature. This is called saturation of magnetization. At saturation, almost all the dipoles in the material are aligned with the magnetic field. It is to be noted that Curie's law is applicable only when the magnetization of the material is far away from its saturation. Properties of paramagnetic materials. 1. A paramagnetic material is very weakly attracted by a strong magnetic field. 2. When a paramagnetic substance is placed in external magnetic field, some of the dipoles inside the material align in the direction of magnetic field. The material is weakly magnetized and acts as very weak bar magnet with north and south pole. Now, the magnetic field lines produced by this material are in the direction of external magnetic field inside the material, and the field lines are opposite to external magnetic field outside the material. The resultant magnetic field will look something like this. The magnetic field here looks as if they prefer to pass through the paramagnetic material rather than air. The magnetic field B inside the conductor is more than the external magnetic field B. 3. Since the magnetic field B inside the material is greater than the external magnetic field B naught, the relative permeability mu r is equal to B by B naught is always greater than 1. The magnetic susceptibility chi m of paramagnetic material varies inversely with absolute temperature. That is, chi m is proportional to 1 by T. The magnetic susceptibility of paramagnetic materials has a small positive value. 4. When a paramagnetic material in the shape of a rod is suspended freely in strong uniform magnetic field, the rod experiences a force and comes to rest in such a way that its longest axis is along the direction of the magnetic field. Ferromagnetism. In ferromagnetic materials, the atoms contain more number of unpaired electrons. For example, iron contains 4 unpaired electrons. Due to this, the net dipole moment of an individual atom is more compared to atoms in paramagnets. The dipole moment of one electron strongly interact with the dipole moment of the neighboring atoms and align themselves in a common direction. This small group of atoms with dipole moments in same direction is called a domain. A ferromagnetic material as a whole is made up of very large number of such domains. In the absence of external magnetic field, the dipole moment of different domains are oriented randomly in different directions. The dipole moment of one domain cancels the dipole moment of other domains, so that the net magnetic moment of the entire material is zero. In the presence of external magnetic field, the domain starts to align in the direction of applied field. The magnetization intensity becomes non-zero. Currently, since the external magnetic field is weak, only one domain has aligned with the external magnetic field. As field gets stronger and stronger, more and more number of domains start aligning with the external magnetic field. The magnetization intensity goes on increasing. Then, for a particular strong magnetic field, the magnetic moments of all the domains get aligned in the direction of magnetic field. Now, the material is at its ultimate stage of magnetization. Now, magnetization does not increase even if the external magnetic field is increased. This stage is also called saturation of magnetization. Just like paramagnetic materials, ferromagnetic materials are also influenced by temperature. When a ferromagnetic material is heated due to thermal energy, the dipole moments within the domain start coming out of the alignment and become random. The randomization goes on increasing. Then, at a particular temperature, the domain structure becomes completely destroyed and the ferromagnetic substance becomes paramagnetic substance. This particular point is called Curie point. Curie point or Curie temperature is defined as the temperature at which a ferromagnetic material becomes paramagnetic material. The Curie temperature of iron is 1043 Kelvin and for cobalt is 1394 Kelvin.
Let's solve the problems based on the competitive examination. The question is, if A is the length of the side of a cube, the distance between the body-centered atom and one corner atom in the cube will be, the given options are A 2 by root 3A, B 4 by root 3A, C root 3 by 4A, and D as root 3 by 2A. In BCC, two atoms are present. One atom lies at the center of cube while other lies at the corners of the cube. Hence, the distance between the body center and one corner atom is half of the body diagonal, that is root 3 by 2 into A. And hence, the given option is option D. The second question is, copper crystallizes in a face-centered cubic lattice with a unit length of 361 picometer. What is the radius of copper atom in picometer? The given options are A 157, B 181, C 108 and D as 128. Let's write down the given data. The unit cell which is present here is face-centered cubic lattice, which is FCC, and a unit length which is given as A, the value is 361 picometer, and hence for FCC the radius formula is given as R is equal to A divided by 2 root 2. Therefore, R is equal to 361 into 10 to the power minus 12 meter, which is 1 picometer, divided by 2 root 2. Upon solving, we get the value of R as 127.6 picometer, which is approximated as 128 picometer. And hence, the right option is option D. The next question is, the radius of Na plus and Cl minus ions are 95 picometer and 181 picometer respectively. The edge length of NaCl unit cell is, the given option are option A 276 picometer, option B 138 picometer, option C 552 picometer, and option D as 415 picometer. The solution is, we know that NaCl has FCC structure.
In FCC lattice, we have R plus R minus is equal to A by 2. Therefore, the edge length A can be given as 2R plus 2R minus. By substituting the value 2 into 95 plus 2 into 181, we get the value as 180 plus 362. Upon adding, we get the value as 552 picometer. And hence, the right option is option C. For tetrahedral coordination, the radius ratio R plus divided by R minus should be, the given options are A 0.4142, 0.732, option B greater than 0.732, option C 0.1562, 0.225, and option D as 0.2252, 0.414. The solution for the above question is, we all know that for tetrahedral coordination, the radius ratio, that is R plus divided by R minus, should be between 0.2252 to 0.414. And therefore, the right option is the option D. The next question is, if Z is the number of atoms in the unit cell that represents close packing sequence ABC, ABC, then the number of tetrahedral voids in the unit cell is equal to, the given options are option A, Z, option B, 2Z, option C, Z by 2, and option D as Z by 4. ABC arrangement of layer is found in CCP system, that is cubic close packing system. In this, atoms are at the corner as well as at the center of the unit cell. Therefore, number of atoms per unit cell is eight into 1 by 8 plus 1, which is equal to 2. Therefore, number of tetrahedral voids in a unit cell is 2 into number of atoms per unit cell, which is equal to Z. Therefore, tetrahedral void is 2Z, and the right option is the option B. The next question is, AB crystallizes in a BCC lattice with edge length A equal to 387 picometer. The distance between two oppositely charged ions in the lattice is, the given options are option A 300 picometer, option B 335 picometer, option C 250 picometer, and option D as 200 picometer. The solution is, for BCC, R plus R minus can be given as root 3 by 2 into A. From the question, we know that A is equal to 387 picometer. By substituting the value of A in the main equation, we get the value of R plus R minus as root 3 into 387 divided by 2, which is equal to 335.15 picometer. And hence, the right option is option B. The next question is, the metal crystallizes with a FCC. The edge of the unit cell is 408 picometer. The diameter of the metal atom is, the given options are option A 288 picometer, option B 408 picometer, option C 144 picometer, and option D as 204 picometer. The solution is, for FCC lattice, we know that 4R is equal to root 2 into A and R is equal to root 2 by 4 into A. And we can also further simplify this equation as A divided by 2 root 2. And from the question, we know that edge length A is equal to 408 picometer. By substituting this value, we get R as 408 divided by 2 root 2, which is equal to 144 picometer. In order to calculate the diameter, we have the relation D is equal to 2 into R, which is equal to 2 into 144 picometer, which is equal to 288 picometer. And the right option is the option A. The question is, the number of carbon atoms per unit cell of the diamond unit cell is, the given options are option A 4, option B 8, option C 6, and option D as 1. The solution is, carbon in diamond crystallizes as FCC, that is, face-centered cubic crystal lattice, and possesses 4 more carbon atoms that are found to be present in alternate tetrahedral voids. Thus, the number of carbon atoms can be calculated by ZF is equal to ZFN FCC plus ZFN alternative tetrahedral voids. Further, let's solve the FCC unit lattice, where 1 by 8 into 8 plus half into 6 refers to FCC unit cell, plus 1 into 4 refers to tetrahedral voids. By solving this, we get the value of ZF as 8. Hence, the number of carbon atoms per unit cell of diamond unit cell is 8, and the right option is option B. The question is, which of the following unit cell having maximum number of atoms? The given options are A BCC, B HCP, C FCC, and D cubic. BCC means body-centered cubic lattice, HCP is hexagonal closed packing, FCC is face-centered cubic lattice, and cubic is the simple cubic structure. Let's calculate for FCC. In FCC, there are 4 atoms per unit cell, which is maximum, and that can be calculated by the formula of number of atoms per unit cell. Eight into 1 by 8 plus 6 into half, which is equal to 1 plus 3, which is equal to 4. And hence, the right option is option C. The question states in this way: silver crystallizes as FCC. If radius of silver is 144 picometer, then its density will be, the given options are A 10 gram per centimeter cube, B 5 gram per centimeter cube, C 15 gram per centimeter cube, and D 6.5 gram centimeter cube. The solution is, firstly, let us convert the radius unit picometer into centimeter by using the conversion factor 1 picometer is equal to 10 to the power minus 10 centimeter. Then for FCC, radius r is equal to root 2 by 4 into a, where root 2 by 4 can be simplified as 0.3535 into a. Therefore, r is equal to 0.3535 a. Now, let us consider the radius of silver. 144 into 10 to the power minus 10 centimeter. Substituting in the above equation, we get the edge length as 144 into 10 to the power minus 10 divided by 0.3535. And the value of A is 407.35 into 10 to the power minus 10 centimeter. And we all know that for FCC, number of atoms per unit cell is given as 4. By substituting this value in the density equation, D is equal to Z into M divided by A cube into Na, where Z is 4, M is the molecular mass of silver, A cube is the edge length, and Na as the Avogadro number. Let's substitute these values in the main equation. 4 into 108 divided by, and the value of A as 407.35 into 10 to the power minus 10 the whole cube into the Avogadro number 6.023 into 10 to the power 23. By simplifying the above numerator and denominator, we get the value of D as 10.6, which is approximated to 10 gram per centimeter cube, and hence the right option is option A. The question is, volume occupied by single cesium chloride ion pair in a crystal is 7.014 into 10 to the power minus 23 centimeter cube. The smallest cesium-cesium internuclear distance is equal to the length of the side of the cube corresponding to volume of one cesium chloride ion pair. The smallest cesium to cesium internuclear distance is nearly. The given options are A 4.4 angstrom, B 4.3 angstrom, C 4 angstrom, and D 4.5 angstrom. The solution is the volume occupied by cesium chloride crystal is given by 7.014 into 10 to the power minus 23 centimeter cube. The volume is nothing but A cube, which is equal to 7.014 into 10 to the power minus 23 centimeter cube. By taking the cube root of this, we get the value of A as 4.125 into 10 to the power minus 8 cm cube, which is further simplified to 4.12 angstrom, which can be approximated as 4 angstrom. And hence, the given option is option C. The next question is, if NaCl is doped with 10 to the power minus 4 mole percent of strontium chloride, that is SrCl2, the concentration of cation vacancies will be, and the given constant is Na is equal to 6.023 into 10 to the power 23 per mole, which is a Avogadro number. The given options are option A 6.02 into 10 to the power 15 per mole, option B 6.02 into 10 to the power 16 per mole, option C 6.02 into 10 to the power 17 per mole, and option D as 6.02 into 10 to the power 14 per mole. The solution is due to the addition of strontium chloride, each strontium ion replaces two Na plus ion. Thus, it creates a cation vacancy. Doping of NaCl with 10 to the power minus 4 mole percent of strontium chloride means 100 mole of NaCl, that is 10 to the power minus 4 divided by 100, which is equal to 10 to the power minus 6 mole. As each 1 mole of strontium 2 plus ion introduces 1 cation vacancy, therefore total number of cation vacancy is 10 to the power minus 6 into Na. By substituting the value of Na, we get 10 to the power minus 6 into the Avogadro number 6.023 into 10 to the power 23 per mole, and the final value is 6.023 into 10 to the power 17 per mole, and hence the right option is option C. The next question is, with which one of the following elements silicon should be doped so as to give p-type of semiconductor? The given options are A. Germanium, B. Arsenic, C. Selenium, D. Boron. P-type semiconductors are obtained when silicon or germanium are doped with traces of elements of group 13. That is indium, boron, and so on. Therefore, the right option is option D. It is a type of assertion question, and the question is, graphite is an example of tetragonal crystal system. The reason are, for a tetragonal system, A is equal to B, which is not equal to C, and alpha is equal to beta is equal to 90 degree and gamma as 120 degree. The given options are option A, both A and R are correct, and R is the correct explanation of A. The option B, both A and R are correct, but R is not the correct explanation of A. The option C, A is correct, but R is incorrect. And the last option, that is option D, both A and R are incorrect. Let's answer this question. Like quartz and ice, graphite is an example of hexagonal system. For hexagonal system, we know that alpha is equal to beta, which is equal to 90 degree, and gamma is equal to 120 degree, and A is equal to B and B is not equal to C. Whereas for a tetragonal system, alpha comma beta is equal to gamma, which is equal to 90 degree, and A is equal to B, where B is not equal to C. Therefore, both the statements are false, and hence the right option is option D. Let's move on to the next question. The cubic unit cell of a metal whose molar mass is 63.55 gram per mole has an edge length of 362 picometer. Its density is 8.92 gram per centimeter cube. The type of unit cell is A. Primitive, B. Face-centered, C. Body-centered, and D. End-centered. Here we have the edge length as A is equal to 362 into 10 to the power minus 10 centimeter, and the molar mass as 63.55 gram per mole, and the density is given as 8.92 gram per centimeter cube. We have to calculate the number of particles per unit cell to decide which type of unit cell it is. Therefore, Z is equal to question mark. From the relation of density, we have the formula as Z into M divided by Na into A cube. By rearranging the terms, Z is equal to D into Na into A cube divided by M. By substituting the values, we get Z as 8.92 into Avogadro number 6.023 into 10 to the power 23 into the edge length 362 into 10 to the power minus 10 the whole cube divided by 63.55. By simplifying, we get the answer as 4. Therefore, the metal crystallizes in FCC unit cell. And the right option is option B. A compound of A and B crystallizes in a cubic lattice in which the A atom occupies the lattice points at the corners of the cube. The B atoms occupies the center of each of the compound is. The given options are option A, A3B, option B, AB, the option C, AB3, and the option D as AB2. The solution is A atoms occupies the corners of the cube, therefore number of atoms of A is 1 by 8 into 8, which is equal to 1. B atoms occupies the center of each of the face of the cube, therefore number of atoms of B is half into 6, which is equal to 3. Thus, probable empirical formula of the compound is A1B3, and hence the right option is option C. The question is, which of the following compounds shows both Frenkel and Schottky defect? The given options are A. NaCl, B. AgCl, C. AgBr, and D. KCl. The solution is AgBr is the compound that exhibits Frenkel as well as Schottky defect. Therefore, the right option is option C. Moving on to the next question, the question is here. The fraction of total volume occupied by the atoms present in a simple cube is. The given options are option A, pi by 6, option B, pi by 3 root 2, option C, pi by 4 root 2, and option D as pi by 4. The solution is, for simple cube, the radius can be given as A by 2, and the volume of the atom is given by 4 by 3 pi r cube. By substituting the value of r in the equation of volume, we get the volume as 4 by 3 pi into A by 2 the whole cube. Therefore, packing fraction can be given as 4 by 3 pi into A by 2 the whole cube divided by A cube. By simplifying this, we get the final answer as pi by 6, and hence the right option is option A. Let's move on to the another variety of problem. The problem states in this manner. The first order reflection n is equal to 1 from a crystal of the X-ray from a copper anode tube whose wavelength is 1.54 angstrom occurs at an angle of 45 degree. What is the distance between the set of plane causing diffraction? The given options are option A 0.1089 nanometer, option B 0.1089 meter, option C 1.089 angstrom, and option D 1.089 into 10 to the power minus 9 meter. Let's write down the given data for the above question. Here we have the reflection as n, which is equal to 1, and the wavelength as 1.54 angstrom, and the angle theta is equal to 45 degree. And we got to calculate what is the distance between the plane, and it is given as d. The relation which satisfies the above data is given by n lambda is equal to 2d sine theta. By substituting the value n as 1, lambda as 1.54 is equal to 2 into d as it is sine of 45. And 1 into 1.54 is 1.54, which is equal to 2 into d, and sine 45 value is 1 by root 2. By simplifying, we get the distance as 1.089 angstrom. Therefore, the given right option is option C. Let's solve the final problem of the session. The question is, percentage of cation in ammonium dichromate is, the given options are option A 41.29%, option B 14.29%, option C 20.29%, and option D none of these. The solution for this problem is, percentage of the element or constituent can be given as number of parts of mass of element divided by molar mass into 100. And we also have molecular formula of ammonium dichromate, which is NH4 twice Cr2O7. From this, we can calculate the molar mass, which comes up to 2 into 14 plus 4 plus 2 into 52 plus 7 into 16, and the total is 252 gram per mole. Now, the number of parts by mass of cation that is ammonium radical, which is NH4 plus, is equal to 2 into 14 plus 4, which is equal to 36. Therefore, percentage of ammonium radical is 36 divided by 252 into 100, which is equal to 14.29%. Therefore, the right option is option B.